Okay, gentlemen, so today I'm going to go over two topics. I'm going to finish up states of matter. I'm going to talk about changes of state, and then I'm just going to introduce the idea of solutions, and that's what we'll do next week. Just to get some idea, we will do 1 week of solutions and concentration, then 2 weeks of what are called thermodynamics, which is energy and chemistry, and then 1 week of pH and acids and bases, and that's it. That's where we'll end up for the rest of the year. So hopefully that will work out. So today I am going to start by talking about changes of state. So for our purposes, there are 3 states of matter. Yes, technically there are a couple others, but we're not going to get into that. There is solid, liquid, and gas. And hopefully you know that. And we've discussed the different, let's spread these out a little bit more, the different properties of each of them. So you should have learned this week a little bit about the different properties of each of them. We did a whole section on gases, and then this week we did solids and liquids. Well, of course, matter can change between these states, and there are names for those state changes. So the first thing I want to do is just cover the names for the state changes. And all 6 state changes exist. So liquid to solid is called, shockingly, freezing. So, and solid to liquid is melting. So you should be familiar with those. That makes a decent amount of sense. The other ones we know pretty well already. Liquid to gas and gas to liquid. Gas to liquid is condensation. That's the name for that. And liquid to gas is called vaporization. Remember, there are 2 types of vaporization. There is boiling and evaporation, but those both count as vaporization. Now, I'm going to talk briefly about 2 other types today in the PowerPoint, and then we'll talk about things like a phase change diagram and triple point, and a couple of terms you might not have been super familiar with. But there are phase changes between solid to gas. It can and does happen, and many of you have probably actually seen it happen, although it's not super common in our everyday lives. So solid to gas is called sublimation, and gas back to solid is called deposition. So there are, in fact, 6 state changes. You can go from any state to any other state, given the right conditions of temperature and pressure. As far as solid to gas, you have seen it probably, if any of you have seen dry ice. Dry ice is called dry ice. It's frozen CO2, solid CO2, carbon dioxide, because it never becomes a liquid, at least not at standard pressures here on Earth. You need to have more pressure to make it a liquid. It goes straight from solid to gas. So it sublimates right in front of you. So that's how dry ice works. And the creation of dry ice generally involves compressing CO2 gas straight into a solid and causing it to deposit. That you probably haven't seen, but that's how that works. So those are the 6 state changes. I just want to make you aware of them. I'm not going to quiz you on this. You could look them up whenever, but I just wanted to make you aware of that. Also, I'm going to quickly go over a couple other things about states, change of state, just to clarify some stuff and cover a bit more before we move on to solutions. So we covered the name of sublimation. This is a picture where you can actually see sublimation. I'm afraid I couldn't do this in the lab, but here we have iodine being heated up. Iodine's pretty cool because it makes a purple gas. It is one of those things, though, if you see a colored gas, you probably want to run the other way. Iodine gas is like chlorine gas. It's pretty bad for you, but in a small quantity, you can do it safely in a lab setting. If you heat up iodine crystals, they turn into a gas, which is what you see here. And what is up here is actually a smaller test tube that has cold ice water in it inside the bigger test tube. And that cold ice water causes that gas not to condense, but to go straight back into a solid. It deposits there. That's what deposition is. So that's deposition. Not something you'll see commonly, but that's what it is. So sublimation and deposition are the 2 gas to solid and solid to gas phase changes. The other thing I wanted to quickly talk about, and I put one on your homework, and it freaked a couple of you out. I just wanted you to briefly describe some basic concepts of it. It's a phase diagram. So phase diagram tells when something, whatever substance, is solid, liquid, or gas at any given temperature and pressure. So every substance would have its own because they all are solid, liquid, and gas at different temperatures and pressures because they have different intermolecular forces. Remember, these things are determined by intermolecular forces versus kinetic energy. Kinetic energy wants to pull things apart. Intermolecular force wants to hold things together. So let's look at a phase diagram. This is a phase diagram for water. I'll move this recording thing. And it has pressure in kilopascals on this side and temperature on the x-axis. So pressure in kilopascals on the y-axis, temperature in degrees Celsius in this case on the x-axis. You could do it in degrees in kelvins; it would be fine. And as you can see, there are three areas: purple, green, and pink, and they represent solid, liquid, and vapor or gas states of matter. So for water, you can follow at standard atmospheric pressure, 101.3. Water melts, turns from solid to liquid at shockingly 0 degrees Celsius. This is its normal melting point. And it boils, it turns from from liquid to vapor at 100 degrees Celsius. This is its normal boiling point. All along these lines, these borders between solid and liquid and vapor, that is a phase change state at all that cases. So you would get boiling anywhere along this line here, and you would get freezing anywhere along this line here, and sublimating and depositing along this line. And by the way, the phase change is the phase change temperature and pressure is that same point going either way. So this is the normal boiling point. It's also the normal condensation point if you're going the other way. Going from hotter to cooler, this is also where you condense, just like the melting point is also the freezing point. The melting point of water is the freezing point of water. So there's this thing down here called the triple point. And the triple point's a really neat thing, and it's where all three states of matter can exist. And in fact, along any of these borders, both states of matter exist. So at 0 degrees Celsius and 101.3 kilopascals standard pressure, you can have both ice and liquid water. It can exist in both states. Just like at 100 degrees, you can have both steam and liquid water. It exists in both states. And that's true all along these borders. Both states can exist. And we'll talk a little bit more when we talk about thermodynamics about how you have to put in energy or take energy out to change the state once you get to that point. But there's a point called the triple point where all three phases exist, or at least potentially can exist in equilibrium. And that's really, really neat. It does happen. It's hard to get to. I've only seen it, well, I did it with water once or twice in the lab when we were screwing around when I was a lab tech. But it's a neat thing to see water boiling and freezing at the same time. That's what a phase diagram is, and that tells you what phase something is at a given temperature and pressure. You'll note, by the way, that liquid is bordered on both sides. That's why liquids are so uncommon compared to natural liquids, compared to solids or gases. Most elements, only 2 or 3 if you count gallium, 3 elements are liquid at room temperature. Most elements are solid or gas. And that's because solid is a solid from this side, kind of the purple area, all the way down, if we were to keep going to the further left, and vapor stays vapor all the way from the phase change from liquid infinitely on to the right. So they're only bordered on one side. They have an infinite distance on each other side. I guess technically solid would stop at 0 kelvins or absolute 0. But still, something's way more likely to be a solid or a vapor because they aren't bordered on both sides. They have a much wider range. So that's the triple point. So here's a picture of the triple point of water. And it's pretty neat. And if you look closely at it, you can see bubbles forming. There's liquid water, and this is a round bottom flask. There's liquid water, and it's boiling. You can see bits of, or bubbles forming where it's boiling. And then on the top, you can see crystals of ice. So ice crystals boiling and literally depositing ice crystals at the top of this flask. it's not impossible to get. It's just to the triple point. It's not that hard. It's fairly low pressure though. You have to have a pretty good vacuum pump. You have to get almost to zero pressure. It's 0.61 kilopascals, which is less than 1% of atmospheric pressure. But it's at 0 degrees Celsius, and that's not that hard to reach. So as long as you have a decent vacuum pump and some good control of the temperature, you can do this. It's an interesting thing to see. If you want, you can look up YouTube videos of it. I haven't found that many great videos of it, but you can, where you can see a lot, but they exist. So again, we have phase diagrams like this, and every substance would have a different phase diagram with different points where it boils and melts and deposits, etc., and sublimates. But this is for water. So I just wanted to go over that really quickly, what a phase diagram was, what it told you, the term triple point, and just make sure you know that there are, in fact, 6 state changes, not just the 4 you think of. You can go straight from solid to gas, and that's called sublimation when going from solid to gas, and going back the other way is called deposition. So I just wanted to make you familiar with those, and now I will talk about concentration. Okay, so I want to introduce the idea of solutions a little bit today. A lot of the chemicals you've used in lab, for the labs we've had, anything that was in a liquid was probably a solution, unless it was pure water. It was something dissolved in water. So solution is a homogeneous mixture. We learned that way back at the beginning of the year in the first chapter when we talked about mixtures and pure substances and homogeneous and heterogeneous. So a solution is a mixture that you can't see the obviously different parts of. Often, when we think of solutions, we think of solutions in water. That is the most common ones we use. But any liquid can dissolve things, and even gases can dissolve other gases. The air is a solution, and technically, the solvent is nitrogen. So all solutions have 2 parts. They have the solvent and the solute. Generally, when we think of solutions, a solvent is what we would think of as water, but it doesn't have to be. The solvent is just what there is the most of. So in the atmosphere, for instance, there's the most of nitrogen, so the atmosphere is a nitrogen solution, which is weird, or a solution of things in nitrogen. Kind of weird to think about, but technically true. The solute is whatever there's less of. There can be more than one solute. You can mix more than one thing in with water. For instance, if you were to make Kool-Aid, you would mix in the Kool-Aid flavor pack, which I think is mostly just coloring, and sugar. And you can control how much sugar you want to put in or don't. But you'd have more water than either other thing. So water would be the solvent, and the sugar and the Kool-Aid pack, they would be solutes. So how dissolving works, especially with liquids, is basically it's an interaction. It's a physical interaction. It's not quite a chemical bond. It's a mixture, so it's not chemically bonded together, but it's a physical interaction. I've kind of drawn out a piece here. So the little red and black dots represent water, the hydrogen and oxygen in water. And remember, one side, the hydrogen side, is slightly positive, and the oxygen side is slightly negative. So water has polarity, which partially determines what it can dissolve. So the properties of the solvent and the solutes determines whether something will be dissolved or not. And let's say that these purple and green dots represent an ionic compound, where the purple is the negative side and the green is the positive side. So what will happen is, if you put that in water, put a chunk of it in water, the water will interact with the cations and anions. The positive part of water will want to react with the negative anion part of the solution, or of the solute of whatever ionic compound you put in there. And it doesn't have to be an ionic compound. There are also polar covalent compounds, but in this case, ionic compound. And the negative side of water, the oxygen side, would want to react, or want to be near, or interact with, I should say, the cation, which in this case I have indicated by the green dots. So the purple dots are positive. Sorry, the purple dots are negative. They interact with the hydrogens. The green dots are positive, and they interact with the oxygen on the water. But either way, that's why ionic compounds are so readily dissolved in water. Something like sodium chloride that has a positive sodium and a negative chloride ion, when you put it in water, those ions will separate and they'll interact with water, because water has a positive side and negative side. So some water will come, surround those things, and kind of separate them all. So a lot of ionic compounds are soluble in water because water is polar. So that polarity of water allows it to interact. There is a limit to how much stuff can be dissolved in water, and it depends on what you're dissolving. And basically, it depends on how much water it takes, how many water particles it takes to dissolve a piece of that thing, and how strongly attracted it is to water as opposed to other things. So salt is pretty soluble in water. In 100 grams of water, you can get like 38 grams of salt, I think. So salt is fairly soluble. But after that, you can't get any more salt to go in the water. If you pour more salt into the solution, it will just sit as a solid at the bottom. So that's what we call a saturated solution, which we'll talk about more next week. So solvent is what there's more of, and for our purposes, generally it's going to be water. It doesn't have to be water, though. I want to make that clear. Not all solutions are based in water. And the solute is what there's less of, so you can think of it as what we're putting into water. And again, it makes a homogeneous mixture. Okay, so I want to talk a little bit more about solutions and just a couple terms to get you used to kind of talking about them. And then we'll get into the math. And there's not a lot of terrible math. You're really kind of peaked at stoichiometry. So as far as the hard math. So solutions are when something is dissolved in something else. It's a homogeneous mixture. And it deals with physical interactions, like I said at the beginning of the video. And generally, we can think of the solvent as water. That's not 100% true, but for a lot of the things we do, it will be true. You have worked in the lab with a bunch of dissolved solutions in water, things that dissolve in water. So I talked about how water has to interact with whatever you're dissolving in it for solution to happen, solvating. So water has to interact with it. And one thing that you can do to speed up something dissolving is make the water move faster. And the reason for that is because when water interacts with something, it'll just sit there. So if I have a salt particle and I put it in water, some water will dissolve the salt right on the edge. So the salt atoms, sodium and chloride ions, right on the edge of the salt. But that water will just sit there until it moves away naturally because of kinetic energy. So while that particle is there, it's kind of blocking all the other particles from dissolving more of the salt. So one of the things you can do to make something dissolve faster, or change the rate of how much something dissolves, is speed up the water. And you can do that a number of ways. And if any of you have ever made tea or iced tea, you probably are aware of this. You can, if you have regular iced tea and you put sugar in it, and the sugar is just sitting at the bottom of the cup, you stir it generally. And that will make some of the sugar dissolve faster because you're bringing in fresh water that hasn't touched the sugar yet to dissolve more new sugar. And the faster you bring in more fresh water on water that hasn't dissolved any sugar yet, the faster it can dissolve more sugar. The other way you can do that is heating. Heating does essentially the same thing. It does it a little more effectively. It speeds up all the particles, so they're moving faster, so they dissolve things more quickly because they interact with them more quickly. Remember, just like chemical reactions, pretty much all physical interactions of chemicals on a molecular and atomic level is just random motion. So the more quickly things are moving, the more likely a water molecule is to run into a solute particle, salt or sugar or whatever you happen to be putting in the water, and interact with it so that it can dissolve. So you can heat something or stir something to make it dissolve faster. You can also grind whatever you're dissolving up. If you take a big cube of salt, or some road salt. If you take some road salt, you can do this at home if you still have some ice melt or road salt from winter. You take a few chunks of road salt and you throw them in water, and you take the same amount of regular table salt by weight and throw that in water. The regular table salt will dissolve faster because the water can get to more parts of it. It has more surface area available. The water can reach the water can't reach the insides of those big chunks of rock salt, so it has to dissolve it layer by layer. The smaller you make the pieces, the less layers there are to dissolve. It can dissolve more of it at once, so it dissolves it faster. So you can also grind stuff up into smaller parts to make them dissolve faster. So that's a couple ways you can kind of deal with solutions and things you probably are aware of. But I just wanted to kind of introduce this before we do it next week, because we're going to spend 1 week on solutions, and that's it. We have to get into thermodynamics and then pH. You won't be even remotely prepared for AP Chem for those of you who are taking it. And I have to at least try. So I want to talk about one more kind of basic idea of solutions, and that is concentration. You can have a solution that has a lot of solute in it or a little bit. And again, if you think of like a Kool-Aid analogy, you can make Kool-Aid with a lot of sugar or a little sugar. And one of them is more concentrated, the one with more sugar, and one of them is less concentrated. So to kind of illustrate what we have going on here, I have a mug, my awesome Xavier mug, and in it there is some food coloring and water. It's just food coloring and water, and it's pretty concentrated. There's a decent amount of food coloring and not that much water. So a decent amount of food coloring and a little bit of water, and it kind of shows as dark because the food coloring actually has a color to it. But if I wanted to, I could change the concentration pretty easily. I'm going to move back and not do this right over the keyboard by adding more water. So if I add more water, what I've changed is the concentration. I have not changed the amount of food coloring. I've changed the concentration, how much solvent there is to the solute, or how much solute there is per solvent. And we have to know that concentration in order to do chemical reactions. So, for instance, when I give you chemicals measured out, when I have given you solutions measured out to use in the lab, you may have noticed the capital M after it, like it would say like 0.1 M hydrochloric acid. That M stands for something called molarity. Excuse me. And molarity measures how many moles you have per liter of solution. It tells you basically how concentrated the solution is. Because really concentrated acid, the 12 molar acid, that hydrochloric acid that I get when we order it, is very different than the 0.1 molar hydrochloric acid that I let you guys use. If you poured 0.1 molar hydrochloric acid on your skin and you went to a sink and rinsed it off, it would be no big deal. Nothing would really happen. If you pour 12 molar hydrochloric acid on your skin, it's going to leave a burn, and if you don't get it off quickly, or if you pour a lot on it, it'll leave a very serious burn, because there's a lot more hydrochloric acid in a lot less space. So concentration matters. And when you dilute something, all you're changing is the amount of solvent, like I did with this. I changed how much water, how much solvent was in here, but I did not change the amount of food coloring, the solute. That stayed the same. And the reason the water is a solvent is because there is more water, and the solute is the food coloring because there's less of it. That's all that determines what's solvent and what's solute, is how much of each thing there are. So that's a quick introduction. You can go over the PowerPoint. You do not have to get into where it talks about gases. I will talk about that a little bit on Monday when we go over stuff. But I'm not going to kill you guys with gases and Henry's law. Just be aware, gases can dissolve in liquids as well. That's what carbonation is, carbon dioxide dissolved in a liquid. And gases can dissolve in other gases. So those are both things that can happen. So go through the PowerPoint today. You don't have any work associated with this, and we'll start with, and we'll have worksheets next week. But go through that PowerPoint 16.1, and hopefully this helped out a little bit, an introduction to concentration and solutions. Okay, have a good weekend, guys.